Hello, ladies and gentlemen. Welcome back to Nuclear Physics. This will be our final SLS lecture for this term. We are going to work on some examples in radioactivity. So can you please turn with me to page 28, where we're going through example 9. Before we go through the example, I would like to recap some very important equations for radioactivity that you can see now on the screen. The first equation is A is equals to lambda n. All right, activity is equals to the decay constant multiplied by the number of remaining nuclei. The second equation is that the half-life is ln 2 divided by lambda. In this case, lambda is the decay constant. The third equations have to do with the exponential decay and talk about the number of nuclei remaining as a decaying exponential, as well as the activity level. Now, on the other hand, you can also say that the remaining nuclei is the original nuclei times half to the power of the number of half-lives. I'm going to illustrate the use of all of these equations in the next example. Let's take a look at example 9. A freshly prepared sample of radioactive isotope contains 10 to the power 23 atoms. Its half-life is 12 hours. Calculate the initial activity A0. Now, to calculate the initial activity A0, we'll use this equation. A0 is equals to lambda multiplied by N0. So the number of atoms that decay per unit time is equal to the probability of decay multiplied by the number of initial atoms. Now, how do we find lambda? Now, we find lambda based on the equation that lambda is equals to ln 2 divided by half-life. Right, so in this case, it will be ln 2 divided by 12 hours. Right, so this is going to give us 0.05776 per hour. This means that there is a 5.7 or 5.8% chance that the nuclei will decay within 1 hour. Now, so once you have the lambda over here, we can get the A0 is equals to lambda to the power times N0. Right? So after multiplying it together, you get 5.78 times 10 to the power of 21 decays per hour. That means this many nuclei are going to decay every hour. Next, how many radioactive atoms remain after 1 hour? So there's a couple of ways to do this. Now, the first way to do this is by using the equation n is equals to n0 e to the power of minus lambda t. From there, you'll get 9.44 times 10 to the power of 22 remaining. Now, there's another way to do it. The other way to do it will be to say that n equals to n0 multiplied by half to the power of the number of half-lives. Now, how many half-life has passed after 1 hour? The answer is 1/12 of a half-life will have passed after 1 hour. So that is also going to give you the same result, okay? And that will be 9.44 multiplied by 10 to the power of 22 atoms as well. Now let's take a look at part 2. Okay, the part 2 question is how many radioactive atoms remain after 12 hours? Well, very simple. Since one half-life has passed, the number of atoms remaining will be 12 times 10 to the power of 23. Now, if you want to use a formula for this, you can use a formula for this. Is n equals to n naught? Well, replace that with 10 to the power of 23, e to the power of minus lambda, 0.05776 multiplied by 12. Multiplied by 12. Okay, so that's going to give you half. Now, you can also do it using the other formula, n equals to 10 to the power of 23 multiplied by half to the power of the number of half-lives. In this case, one half-life has passed, 12 over 12. Now, you can also do the same for the third part. The third part says after 24 hours. So n equals to n0 multiplied by half to the power of the number of half-lives, 12 over 24. Okay, so this will give you the correct answer as well. Now, let's take a look at the next example, question 10. A radioactive source has decayed to 1/128th of its initial activity after 50 days. What is its half-life? Okay, so there is a way to do this easily. Okay, so this is the long way to do it. I think this is the long way to do it. Okay, the long way. Now, the long way to do it uses this equation. A is equals to A0 e to the power of minus lambda t. So we're going to write down 1 over 128. Okay, this is the activity level. Okay, this equals to e to the power of minus lambda, and the time is 50 days. Now, if you do a ln of both sides, you get ln 1 over 128 is equals to minus lambda 50. And that is going to give you lambda is equals to 0.097 per day. That means to say you have a probability 9.7% chance of decaying every day, right, for our nuclear. Now, so then you can then use the equation half-life is equals to ln 2 divided by lambda, which will give you 7.1 days. Okay, so this is the long way of doing it. Now, what is the short way of doing it? Now, there's another short way of doing it, which is to use the other equation. A is equals to A0 multiplied by half to the power of the number of half-lives. Okay, number of half-lives. So let's try this. So the activity level is 1 over 128, which is half to the power of the number of half-lives. And well, if you use a calculator, you'll find that the number of half-life to pass, number of half-life, okay, that have passed, n is equals to 7. So that means 50 days is equals to 7 half-life. So then a half-life will be equals to 50 divided by 7 days, which is 7.1 days. Okay, so you can use both equations. You can use the exponential format, or you can use half to the power of number of half-lives. Now, when do you use which equation? I would generally say that when given the number of half-life, okay, use the second equation, which is the equation that deals with A is equals to A0 multiplied by half, okay, to the power of the number of half-lives. Okay, so this equation is generally easier if you are given the half-life. Okay, if you're given a decay constant, of course you can use the first equation. Right, so this is example 10. Now let's move on to example 11. Living wood has an activity of 15.4 counts per minute per gram of carbon. A certain sample of dead wood is found to have an activity of 17 counts per minute for 5 grams. Calculate the age of the sample of the dead wood. Assume that half-life of carbon-14 is 5730 years. Now, this system is called carbon dating, which I have explained in my previous SLS lecture, lecture number 3. So if you don't understand what carbon dating is, please go take a look at the previous lecture. All right, it's given by a guest speaker. Now, so first of all, we will need to compare the activity level for a gram of carbon. So this is the living wood. Now the living wood is 15.4 per gram per minute. Per gram per minute. Right. This is the activity level of the living wood, which we can call it is the activity level which you're supposed to have. Okay, 15.4 gram per minute. Now, what about the wood that's been dead? This is the ancient wood. Now, the ancient wood activity level, which is the current activity level of the ancient wood, we have to take a look at how to access it. It's 17.0 per minute for 5 grams. So we need to reduce it to a single gram of wood because 17 counts per minute refers to 5 grams of the wood. So this will be 17 divided by 5 per gram per minute. All right. So that would be equals to 3.4 counts per gram per minute. So you can see that the living wood originally, I mean, assuming that the level of carbon 14 in all living woods is the same for the entire history of the world, right? It's 15.4 grams, 15.4 per gram per minute. That should be the original level. The ancient wood now has decayed to 3.4. So now we can find out how many half-lives have passed. Now you can take a look at the original way of doing it. Now the original way of doing it, which is shown on the left, will be A is equals to A0 e to the power of minus lambda t. So they want to find t. Okay, so they first have to find lambda. Lambda is equals to ln 2 divided by 5,730, right? So this will give us 1.21 times 10 to the power of minus 4 per year. That means that your chance of decaying is this much per year. And then in that case, we can solve the equation by using the A equals A naught e to the minus lambda t. You can put in 3.4, which is the current activity level. This is the original activity level of living wood minus 1.21 times 10 to the power of minus 4 t, and you solve it to get t is 12,500 years. Okay, now there is a different way of doing it, of course, using the other equation, which is the number of half-lives. So what we can do is that we can use A is equals to A0 half to the power of the number of half-lives, which we call n. So we can fill in here 3.4 is equals to 15.4 multiplied by half to the power of the number of half-lives. From this, we can get the number of half-lives is 2.179 half-life. That means that the number of years, the time that has passed, will be 2.179 multiplied by the number of years in the half-lives, which is 5730. And that would also give us the same result, 12,500 years. Okay? So this is an example of how you can use both equations to solve for the time that has passed, in terms of carbon dating. Now, for the next part of the lecture, I want to go back to this part over here called background radiation. Okay. Now, there's going to be radiation coming from all kinds of sources. One of the most important radiation sources is, of course, the sky, since there's a lot of cosmic radiation, and that kind of sets off the detectors. The other important source of radiation is from the ground. Now, very old rocks such as granite contains significant amounts of radiation. Okay, these are rocks that have been formed for many, many millions of years, and they were originally radioactive when the Earth was formed. So, if you have any granite countertops or granite furniture, or your house is made of granite, which is not possible in Singapore, you may actually be exposed to quite a lot of radiation. Now, how does background radiation affect the measurement of radiation? Now, background radiation will have a flat uh, increase in your radiation level. So, for example, let's take a look at this situation. Now, over here we have a rock, right, sitting on a table. And then over here there's a detector. Now, this detector detects 114 activity level of 114 becquerels, 114 per second. Okay, now without the rock, right? This sensor itself detects a base activity level of 14 per second. Now, what this means is that the rock actually, the corrected count rate is actually 100. So we call this the count rate. Uh, sorry, we call this the background radiation. So this is the background will be 14 becquerels BQ. Then over here we have the count rate. The measured count rate is 114 becquerels. And then we do what is called a corrected count rate. Now the corrected count rate, the corrected count rate is actually 100 becquerels, which is 114 minus 14. All right. Now, so let's see what happens after a half-life. After two half-life, okay, have passed. This is after two half-life has passed. What will the detector detect? Now, after two half-life has passed, the corrected count rate, which is the actual activity level of the rock, will be 25 becquerel. But what is shown on the sensor, this is what the sensor will read. The sensor will read the count rate. And how much is the count rate? The count rate, you have to add the background radiation back again. That will be 39 becquerels. Okay, so this is how to deal with the background radiation in terms of correcting the sensor reading. Okay, so the background radiation has to be dealt with in this way. First of all, take the count rate minus the background to give you the corrected count rate. Now, second of all, use the corrected count rate to calculate the new count rate, the new CCR in the future. Okay, and then after you have found the corrected count rate, the CCR plus the background radiation back again will be your count rate that is expected on the sensor. Okay, so there are three steps in order to use the background radiation reading. Okay, you have to take the count rate, which is the one including background. You take away the background first, then you do all the radioactive decay equations, how many half-life has passed. Then after that, you add back the background radiation to get the sensor reading, which you expect to get. All right. So this is background radiation. Now let's go back a couple of pages. All right. I want to go back a couple of pages, page 26, to radioactive treatment in medicine. Okay. Radiation dose in medicine. Okay. So we're going to talk about now how you calculate, or rather, how radioactive uh, chemicals are used in medicine, and how do you have to consider how much radiation does each person get. Now, roughly speaking, the amount of the dose of radiation is given by your activity level of the radioactive substance multiplied by time of exposure. So for example, let's say your activity level is 114 becquerels, which means 114 per second. Then you multiply it by the time of 60 seconds, okay, times 60 seconds. So this will be your dose. So that would be your number of radioactive, rays or particles that you are exposed to. So what happens is that if your radioactive substance is a bit older, all right, so if the chemical that is used for the radioactive treatment has been decaying for a while, for a certain time, then the activity level will be lower. Now, if the activity level is lower, then the patient has to be exposed for a longer time to get the same dose. Does it make sense to you? Okay, so the dosage is the activity level multiplied by time. If the chemical radioactive medicine has been decaying for a certain time, then its activity level is lower. Then if you use that chemical, which is less radioactive, the patient will have to be exposed for a longer time to get the same dose. Okay, now we're going to go to some additional questions in your tutorial that will highlight some of these issues. Do you mind opening up your tutorial with me? Okay, we're going to go to the nuclear tutorial, and then we're going to look at the additional questions that are way at the back. Okay, way at the back. We're going to go to the additional question number 27. Okay, 27. Okay, let's take a look. In a cancer therapy, okay, are you guys there yet? You can always pause the video and then, while you're frantically flipping the pages, you can restart the video once you're ready. Okay? Now, in a cancer therapy, patients are given treatment from a radioactive source. The source has a half-life of 4 years. Now, if a particular treatment requires 10 minutes of radiation when the source is first used, how much time is required for the same treatment if the original source is used 2 years later? Okay, so let's take a look now. So uh, the original dose will be like the original activity level multiplied by 10 minutes. Okay, so what happens if the medicine has been left decaying for 2 years? Okay, then the new activity level will be much lower. So the new activity level will be the original activity level multiplied by half to the power of the number of half-lives. Now, how many half-life has passed? The answer is 2 of 4. Half a half-life has passed. What a funny thing to say. So the new activity level will be 0.71 A0, which means to say it's down to 71% of the original activity. Now, if the activity has decreased to 71%, then the time must increase to 14 minutes. How do we do this? So the same dose, okay, is going to be achieved using the following way. First, we take the 0.71 A0 multiplied by the new time T2, and this must be equals to A0 multiplied by 10. So let's take a look. 0.71 A0, which is 71% of the original dose, multiplied by the new exposure time, gives us as much radiation as the original activity level multiplied by 10. Okay, so we can see now that the T2 is equals to 10 divided by 0.71, which is 14 minutes. So because the original dose has gone down, original activity has gone down to 71% of its, uh, the medicine has gone down to 71% of its original activity. You got to extend the dosage time, okay, to get the same dose. Right, so this is how this question will work. Now, next question, question 28. This question is about the background radiation. Okay, a radioactive source contains a nuclei 187 tungsten, which has a half-life of 24 hours. In the absence of this source, a constant count rate of 10 per second is recorded. This is the background radiation. Immediately after the source is placed in a fixed position near the counter, the average count rate rises to 90 per second. This is the count rate. When the what average count rate is expected with the source at the same location 24 hours later, i.e. one half-life later. Okay. Now, so the steps in solving this equation will be, okay, take the count rate minus the background radiation to be the corrected count rate, CCR. So we take 90 minus 10 gives you the 80 per second. Then after that, the corrected count rate will be 1 times half-life later. Sorry, what am I writing? 1 half-life later. The corrected count rate will be 40 per second. From 80 per second, it dropped to 40 per second. So then the count rate will be the corrected count rate plus background. You add the background radiation back to see what you're going to get on the sensor. All right, so that is the sensor is going to read 50 per second. Now, the background radiation is actually quite significant. We are going to read about 14 activities per second, 10 to 14 per second in almost any location on Earth. All right, so we're exposed to quite a lot of background radiation. So I hope you remember how to deal with background radiation now. You take it away from the count rate to get the corrected count rate. Then you apply your decay laws to the corrected count rate. You add background radiation back to estimate what you're going to read on the sensor. Okay, next and the last question, all right, is over here. Potassium 40, an isotope of potassium, has a half-life of 1.37 billion years and decays into an isotope of argon, which is stable. In a particular sample of moon rock, the ratio of potassium to argon atoms is found to be 1 to 7. Estimate the age of the rock, assuming that originally there's no argon present. State one other assumption which you have made in your calculation. Now, let's take a look. Okay, first of all, we are going to write down this is the potassium, and then it's going to uh, decays into an isotope of argon, which I don't know what isotope of argon it is, better not write 40. Okay, and then we're going to write like the number of half-lives. Okay, number of half-lives. Okay, so this is at the start. At the start, okay, it's 100% potassium and 0% argon. So the ratio of potassium is to argon is 100 is to 0. Now, next, let's, uh, after one half-life has passed, how much potassium is remaining? 50% of the potassium has decayed, and now the sample has decayed, and 50% of the sample is now made of argon. So the potassium to the argon ratio is 1 to 1. What about after two half-life has passed? After two half-life has passed, the number of the percentage of the sample that is still potassium will drop to 25%, and the percentage of the sample that goes to argon is now 75% argon, up from 50%. So the ratio of potassium to argon is now 1 is to 3. Does it make sense? Okay, now after three half-life has passed, it's now 12.5% potassium and 87.5% argon. Now, if you do the ratio, divide it through, you're going to get something like 1 is to 7. So a 1 is to 7 ratio of potassium to argon means that three half-lives have passed. Okay, three half-life has passed. So if three half-life has passed, then the time that has elapsed, time will be equals to 1.37 times 10 to the power of 9 billion years multiplied by 3, which is 4.11 times 10 to the power of 9. Now, what is the other assumption that you have made in your calculation? One other assumption that we can make in our calculation is that potassium 40 does not come from any other source, right? So one other assumption that we can make is that potassium 40, okay, does not come from any other source. Well, because if potassium 40 is continuously being generated by some cosmic event, then of course it won't be just decaying, it will be being decayed and then being produced at the same time. So the calculations will all be confused. Now, perhaps you want to uh, also, well, okay, I guess that's one of the main assumptions that we're going to make. Okay? All right, so this is question 21. And with that, we've officially come to the end of nuclear physics. All that remains next term is that we will go through some of the questions again, and I'll just do a refresher, since I'm sure you probably would forget a lot of nuclear physics during the holidays. So that's the end, and I hope you enjoyed this video. Okay, thank you and have a nice day.